Okay, chapter 5. It's the harmonic oscillator and vibrational spectroscopy. So in the previous chapter, we established the fundamental postulates of quantum mechanics. And in this chapter 5, we will apply this principle to a critical and very important model in chemistry, the harmonic oscillator. So as I mentioned in the orientation of our lecture, there are 4, maybe 5 toy models that we can solve exactly. The harmonic oscillator is one of them. So we discussed the particle in a box at chapter 2 or 3, I guess. And now we are going to meet harmonic oscillator, which is the second toy model. So in this chapter, we will cover several key topics. The first is we are going to start with a classical harmonic oscillator. Classical harmonic oscillator. So which you may remember from introductory physics. Maybe you learned the classical harmonics in the freshman physics class. Then we will apply our quantum postulates to develop the quantum mechanical harmonic oscillator. So quantum harmonic oscillator. And this will lead us directly to understanding the infrared spectrum of diatomic molecules. So infrared spectrum. And we will derive the selection rule that governs which vibrational transitions are allowed. So selection rule. And finally, we will extend these concepts to more complex systems by introducing normal coordinates. To describe the vibrational motion of polyatomic molecules. This sounds quite interesting, right? Okay, section 5.1, the harmonic oscillator obeys Hooke's law. So let's begin with the classical picture. Imagine a simple system, something like a mass M. The particle is connected to a stationary wall by a spring. So there is a wall here, and they are connected by a spring. So when the system is at rest, the spring has an equilibrium length, which we will call L0. If we stretch or compress the spring to a new position L, like let's say that we stretch the spring, and now we have a new position, new length. So we create a displacement x, right? This is defined as the difference between the new position and the equilibrium length. So this system obeys a fundamental principle known as Hooke's law. Hooke's law. This law states that the spring exerts a restoring force, F, that is directly proportional to the displacement x. So mathematically, we will write as, let's introduce the force constant K, F equal minus Kx. So here K is force constant of the spring, which is a measure of which is a measure of the spring's stiffness. So the negative sign here, this denotes this force is exactly opposite to the displacement. So this means the restoring force. So if you stretch the spring like positive X, the force pulls it back. And if you compress it, then which means the negative X, then the force pushes it forward. Right? So the displacement and the force direction is opposite. So that is covered by this negative sign. And I want to describe the motion of this particle over time. So now we are going to use the Newton's second law of motion, F equal Newton's second law of motion, F equal ma. Here the acceleration a is the second derivative of the position with respect to time, right? A is simply the second derivative of time for a function, for the position. So combining the Newton's second law of motion and Hooke's law, we can set up the equation for the position x. So actually we are dealing with its length, right? Because we are interested in the position of mass m. That means we need a value for the position L, right? So I'm sorry, I have to rewrite this part. So here the acceleration should be like this. Even though the x still denotes the position x, right? But we need a more precise expression because the position of the mass m is described by its length L. And here the restoring force X is defined as the L minus L0. And we want to make this equation a little bit more easier to solve. So let's replace this part with X. And fortunately, X is the L minus L0. So L0 is the equilibrium length, which means that it should be the simple constant. So if we take the derivative and second derivative of the position x, that means this part, equilibrium length part, should be gone. So mathematically, it doesn't really matter whether we focus on the length L or the displacement x. So if we solve the differential equation for the position x, and then we can convert this information to the position L by adding the equilibrium length L0, right? So the governing equation for the simple harmonic oscillator is something like this. And we can solve this simple differential equation, right? This is the example of the first order linear differential equation. So you know that the general solution to this differential equation is simply x equal This is the linear combination of sine function and cosine function. The both sine function and cosine function can satisfy this differential equation. In this case, we have to take the linear combination of all possible solutions, right? So this solution describes an oscillation because both sine function and cosine function oscillates over time with a period of 2 pi. And here the omega, this is angular velocity. So you all know, now understand what the angular velocity means, right? How fast it makes circle. How many circles it makes in second. So with related to the original differential equation, so omega should be defined as the square root of the k over m. But there is one loose end. We have to determine these two constants, C1 and C2. And these constants depend on the initial condition. So if we think of the motion of harmonic oscillator, at least we can say there are two conditions we know exactly. The first condition is when we stretch the spring to a maximum displacement, we call the displacement is A. Usually we use the A for amplitude. So at time t equals 0, the position of x should be A, right? So plugging this initial condition into our general solution, that means that should be equal to A. And sine 0 should be 0 and cosine 0 should be 1. That means we can determine the second constant, C2, as A. The second initial condition that we can use is, let's think about the situation like this. So we release the mass from the rest, meaning its initial velocity should be 0, right? So the system is at rest and there is no external force, and its initial velocity should be 0. So the velocity is the first derivative of position, dx over dt. And from our general solution, the velocity should be given as c1 omega cosine omega t minus c2 omega sine omega t. So at time 0, so we don't have the sine term anymore, and c1 omega multiplied by 1 should be 0. So angular velocity is not 0 here. This cannot be 0. That means the constant c1 should be 0. So substituting these two constants back into the general solution gives us the specific equation of motion for our model system. So for xt, A cosine omega t. So this equation elegantly describes the oscillating position of the mass over time. This classical model is the foundation we will build upon understand how molecules vibrates, which is a purely quantum mechanical phenomena. That is why we have to understand the classical physics first, and we need to move on to the quantum mechanics. Okay, the next section is 5.2. The title, let's just mention the title and skip. I'm going to skip this part. The energy of a harmonic oscillator is conserved. It is quite trivial statement, right? We all know this statement from the middle school science class. The energy is conserved, and especially for a harmonic oscillator, the total energy is conserved, and it just changes its form, like from kinetic energy to the potential energy, and from the potential energy to the kinetic energy. So we are not going to discuss in detail, and you can read this part by yourself. Okay, let's move on to the next section. Okay, section 5.3, the equation for a harmonic oscillator model for a diatomic molecule contains reduced mass of molecules. So 3 important keywords, the harmonic oscillator model. And we can apply the harmonic oscillator model for a diatomic molecule case, which means the molecule containing 2 atoms. And that equation, that governing equation contains the reduced mass. It is quite similar to when we discussed the Bohr's hydrogen atomic model. So we can consider the nucleus as the fixed mass, but the accuracy in predicting the Rydberg constant can be improved by considering the reduced mass, right? So actually, even though the nucleus of the hydrogen is much heavier compared to the electrons, but it still has the finite mass. That means the nucleus can still move a little bit, right? So it is very similar to that. So we are going to discuss the diatomic molecule. So if you introduce the reduced mass, then you are going to have a much more accurate description for this problem. So in the previous section, we described the Hooke's law with one particle connected to a fixed wall, right? In graphically this can be drawn like this. But actually we are going to discuss the diatomic molecules. That means there is no fixed end. 2 masses are connected by the spring. So unlike the previous case, both masses are now free to move. So we will denote their position along the x-axis as x1 and y1. So let's say, so we have the coordinate system here. So this is the x-axis, and this is the x1. Displacement is x2. So we have the particle with mass m1 and m2 for each position. And for sure, the distance between 2 particles, 2 atoms, should be denoted as L0. So L0 is the equilibrium length between 2 atoms. And let's write down the equation of motion for each mass using Newton's second law. So for the first particle, I'm sorry, I have a very bad condition. So force on mass m1 is proportional to the bond displacement. So particle 1. So displacement is the x2 minus x1 minus L0. So pulling it to the right if the bond is stretched. So its governing equation of motion should be So you might wonder why do we miss the negative sign here? Let's talk about that later. And we have another particle here, particle 2. So they are connected to the one spring. That means the magnitude of the force should be same because they are connected to the one spring, but their force direction should be opposite. So the equation of motion the same force but with the negative sign. Since these two particles are connected to one spring, if the spring is stretched, that means they tend to restore back to its equilibrium position, and that means one particle should move to the left and one particle should move to the right. So their force direction should be opposite. That's why we have the negative sign for the one particle and we have the positive sign for the other particle. So please do not focus on the negative sign itself. Please focus on the meaning of the negative sign. It is the representative of restoring force. Okay? So it simply denotes the direction of the force. Okay? I hope you understand this point. So the problem is now we have two particles and therefore we have two equation of motions. So two-body problem looks much more complicated than our single-body problem that we discussed in the previous chapter. However, we can simplify it by separating the motion of the molecules into two parts. Separation of motion. So overall motion of the entire molecule through the space, which should be the translational motion, and the internal motion of the atoms relative to each other. The second is vibration. Okay, first let's look at the translation. So it is quite straightforward that we can separate the motion into these terms. So let's think just this is the diatomic molecule. So they can move in the space, right? Which means that their center of mass can vary in the space. That is the translation motion. And even without the translational motion, they can move, right? Which means at the fixed center of motion, these two particles can vibrate. That is the vibrational motion. So we can separate these two motions. So let's focus on the translation motion first. So if you take a look at the first and the second equation of motions, you may realize that the right hand side of these two equations can be cancelled out, right? If we add up these two equations, then the right hand side will disappear. So that's right. And the mass is simple constant, so we can put this simple constant into the differential operator. Let's do not jump to there. And you might remember that the differentiation operator is the linear operator, so it doesn't really matter the order between the linear differential operator and the add or add operation. So you can take the derivative first and add up these two terms, or otherwise you want to add up the content first, and you can take the derivative of that total sum. And now you might want to divide and multiply by the same number at the numerator and denominator, the total mass m. So this is simply just 1, right? But if we put the denominator into the differentiation operator, the equation becomes the expression in the differentiation operator, this is exactly the mathematical expression of center of mass. And what does this equation imply? The left-hand side is the Newton's second law of motion for the equation of motion, right? I'm sorry, Newton's second law of motion for the center of mass, x, with total mass, capital M. And this motion does not have any external force. So the center of motion moves at a constant velocity, and this describes the translational motion of the molecule as a whole moving uniformly through the space. So if you want to describe the translational motion of a diatomic molecule, you don't really know about the vibration part. You can just consider them as a one large mass, capital M, given as the sum of the two particles. So translation part is quite straightforward. And let's go to the vibration part. And vibration part. To describe the internal motion, we define a relative coordinate x, relative coordinate x, which represents the deviation of the bond length from its equilibrium value. So x should be defined as the x2 minus x1 minus L0. So this should be the length between two atoms at the arbitrary moment. And to get an equation of motion just for x, we can manipulate our original equation. So if we divide the equation, the first this equation, let's rewrite. So we have two particles and we have two equations of motion. I just simply rewrite the previous expressions. So now we are trying to take the subtract between these two terms, because we want to focus on the difference between the two positions, x2 and xl, because this represents the length between two masses. And first of all, so I want to divide the first equation by m1, and I want to divide the second equation by m2, and I want to subtract the second equation from the first equation. So let's take the step by step. And as I mentioned, we want to focus on the length L, which can be calculated from the difference between x2 and x1. So that means there should be minus k here. Okay, so now we combined two equations of motions into one. And let's refine this equation a little bit more. So let's take a look at this part. So x2 minus x1, this is simply taking the measure. We want to measure how the position of the two atoms deviate from the equilibrium length. So this should be equal to the L0 plus x. And as I mentioned when we discussed the one-body problem, so taking the second derivative for the constant doesn't have any meaning. So the left-hand side will be reduced to d square x over dt square. And still there is some complex part. And what about the right hand side this part. So according to this relation, this should be exactly just x. So this equation looks a little bit more familiar or more similar to the one particle problem. But this part is a little bit more complicated. But if we define the reduced mass represented by the Greek letter mu, which is defined as then this equation should be reduced to minus k over mu x. So if we rearrange this relation, the mu multiplied by minus kx. Actually, this is quite important consequence because remember that we started from two equation of motions for the particle 1 and particle 2, but with some mathematical manipulation, we obtained one equation. And actually this describes the time evolution of position x, and x is related to the deviation from the equilibrium length. So deviation from the equilibrium means that this motion describes the vibration, right? So this is the equation describing the vibration, and there is another important factor. So now we have the mass mu. So mu is the reduced mass, which is defined something like below. So if we described what we have done in graphically, so we have two bodies with finite mass, and by introducing the relative coordinate x and reduced mass mu, now we have some system like this. So we reduce the two-body problem to one-body problem, which is much easier to solve. And we already solved this type of general differential equation, right? So this is the starting point of discussing harmonic oscillator. Let's go one more section. Section 5.4. So the harmonic oscillator approximation results from the expansion of an interatomic potential around its minimum. So quantum mechanical harmonic oscillator is the fundamental model we use to understand the vibration of a diatomic molecule. So it is important to recognize from the outset that this model is an approximation. So let's explore why we use it and when it is appropriate to use this harmonic approximation model. So let's draw the potential energy surface of some diatomic molecule along the distance between them. And when they are far apart, let's take the reference energy as the sum of two atoms' energy. And their orbitals start to overlap, and we have some energy stabilization due to the orbital overlapping. And finally, they find some favorable spot, which represents the molecular geometry. And when their nucleus get too close, and their energy diverges. So normal potential energy surface looks like this. And if we apply the harmonic oscillator approximation, which means the potential energy of the B is simply the half of the kx square. This simply like this. The parabola here. The yellow color parabola here. So let's look at the characteristics of the Lear internuclear potential and compare that with the harmonic oscillation. So for the small internuclear distance, this part, so the potential energy rises very speedily for the Lear molecule. So this is due to the powerful electrostatic repulsion between two nucleus. And the large internuclear distance, the curve initially rises, but then saturated at some point. This is quite different from the harmonic oscillation model. So you can clearly observe that only the harmonic approximation can be applied is the vicinity of the minimum of the potential energy surface. Then why is it like that? So we can justify the harmonic approximation with a Taylor expansion. So you already learned how to apply the Taylor expansion for arbitrary function f. And let's say you want to expand the potential energy B around the equilibrium bond length L0. So this point should be L0. So that means the BL should be the sum of its function's value at L0, and you are going to add the first correction, and you want to add the second term, and this is like infinite sum. So we are going to stop at the third order. So let's simplify this expression term by term. So this is the absolute energy, potential energy at L0. But in chemistry, we are not really interested in the absolute energy. So absolute energy doesn't really matter. So we can take this term as just 0. And what about the first derivative? So we are now trying to expand the potential energy near the equilibrium region. That means near the equilibrium region, the slope at that point should be quite close to 0. So we can approximate this term also 0. Then what is the first term that appear, that remain? That is the second term, right? So finally, this expression can be reduced to and we can ignore the higher term because they wouldn't be as important as the second term. So this second derivative represents the curvature of your potential energy work. And what about this? L minus L0. This is simply the displacement. So that's why we write this equation something like this. So this is the harmonic oscillator approximation, right? This simply involves the truncating the Taylor expansion series after the first non-zero term, and by ignoring the third and fourth higher term, we can obtain this expression. So I guess we are going to discuss this part later, and this part is anharmonic term. So the quadratic term is known as the harmonic term, and the cubic is anharmonic term. So this plays also very important role in vibrational spectroscopy. So we are going to discuss that this Wednesday.